In this example, I'm going to show you how to find odd complex zero of the function f, and we're going to rewrite the function f in the completed factored form. First, I'm looking for the degree of the polynomial n. A degree is 4 because 4 is the highest exponent in a polynomial. That means that this function have 4 complex zeros. Now first I'm going to find the constant coefficient. Our constant coefficient is a minus 10. So therefore P, to find P stands for the factors of the leading, the factors of the constant coefficient. 10 can rewrite as 1 and 10 or 2 and 5. These are 4 possible factors of 10. So I have 1, 2, 5, and 10. I want to all the possible of factor of 10. I can have plus or minus here to guarantee that I have all the possible. So now it's plus or minus there. Now our leading coefficient is 6 because right here is our leading coefficient, which belongs to the highest, the term that has the highest exponent, which is now we're looking for the list of factors of the leading coefficient. 6 can rewrite as 1 and 6, 2 and 3. So I have 1, 2, 3, and 6. Now to guarantee that I have all the possible factors, I will have plus or minus. Okay. Then to list all the possible rational zeros, which is stand for P over Q. The easy way to do is I'm going to take each number of Q and put over, take each number of P over each number of Q. And then from there I proceed. So I have, for now, I'm not too worried about the plus and minus sign yet. So how 1 over 1 is 1. Then how 1 over 2 is 1/2. Then continue our 1 over 3. And then 1 over 6. Then put 2. Put 2 over 1 is 2. Then 2 over 2 is 1. But I already have 1 over here already, so I don't need that. So I put 5, gives me 2 over 6. Wait, what I miss? Let's try again. 2 over 1 is 2. 2 over 2 is 1. But we already have 1 here, so I don't need that. But rewrite again. So then 2 over 3. And then 2 over 6. Now 2 over 6 is 1/3. But I have 1/3 over here already, so I'm going to cancel it now. I don't need this. I don't need only 1/3, not 2 of 1/3. Now I put 5 over 1 is 5. 5 over 2. 5 over 3 and 5 over 6. Now I'm going to continue to number 10. 10 over 1 is 10. 10 over 2 is 5. 10 over 2 is 5, but I already have 5 here, so I don't have to copy it down. So 10 over 3, and then 10 over 6. 10 over 6 can simplify as 5 over 3, but this is the same as this guy, so I just erase this. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12 on the list. So P over Q should be plus or minus 1, plus or minus 1/2, 1/3, and just continue on. I add all the plus or minus to the list to guarantee that I have all the possible factor. We have positive and minus 10, and the last one. This Q over P here mean that if F have, it mean that this it said that if F has a rational 0, then this must appear on the list. On this list. So this is give us the possible rational list of possible 0. So in other words, if F have any solution, it must appear among this list here that we found. The next step, we have to go through the list to evaluate each number, or we using the synthetic division until we find a 0. And remember that if F of Q, P over Q is 0, then P over Q is a 0 of the polynomial. So now if I go to this list here and pick out any number here and evaluate F of that number equal to 0, then that number must be the solution of my polynomial. This is one way to do it. Or the easy way to do is we using the synthetic division until we find a 0, and then that's how it's actually faster. So I'm using the synthetic division to do that. So here is I pick 1, a positive 1, and I list all my coefficients of my polynomial f, which is over up here. Is my polynomial, and I'm using the synthetic division. And to do that, and draw a line and always bring the 6 down. Take 1 times 6 is 6. 13 plus 6 is 19. Then take 1 times 19 is 19. 61 plus 19 is 81. 0 times 80 is 80. 8 plus 80 is 88. 0 times 88 is 88. Plus or minus 10 is 7. I'm sorry. Yeah. Now, because this is last number here stands for our remainder, since our remainder is not 0, so therefore 1 is not our solution, or it's not a 0 of our polynomial. So I'm going to move on to minus 1. So let's move on. Using -1, I have 6, 13, 61, 8, and -10. So I'm going to bring the 6 down. -1 times 6 is -6. 13 plus -6 is 7. -1 times 7 is -7. 61 plus 7 is 54. -1 times gives me plus. -1 times 54 is -54. I add 8, I get -46. -1 times -46 is positive 46. Add -10 is 36. Because this is not a 0, based on the factor theorem, -1 is not our 0 or our solution. So we continue on. So that means that I test here, this number 1 here is not good. So I cross out. Now I'm going to try 1/2 and do the same thing. This method is quite quick. So if you using the synthetic division, so I have 6, 13, 61, 8, and -10. So I bring the 6 down. 6 times 1/2 is 3, plus 13 is 16. 1/2 times 16 is 8, plus 61 is 9. 1/2 times 69 is 34, plus 5, plus 8 is 42.5. 1/2 times 42.5 is 21.25, plus -10 will be 11.25. Because this is not a 0, so therefore positive 1/2 is not our it's not a solution. So let's try a -1/2. Bring a 6 down. -1/2 times 6 is -3. Add 13, I got 10. -1/2 times 10 is a -5. Plus 61 is 56. -1/2 times 56 is -28. Plus 8 is -20. -20 times -1/2 times -20 is a positive 10. Plus -10 is 0. Voila. That means that -1/2 is our solution, or a 0 of our polynomial. That means that if I put f of -1/2 inside my function, I will get a 0. It's equal to 0. So -1/2 is a 0 of our polynomial. So we can rewrite f of x as a factor form. We have x minus, but -1/2 become a positive. And then this is our new factor here. So we have x to the cube plus 10 squared plus 56 minus 20. It gives me 56x. 20. That's our factor.